Hi everyone, my name is Anna and this is my class presentation for the discipline CE565. Today I'm going to talk about time effects on strength and deformation of subgrade soils. Here is a brief introduction. A soil under a long-term stress changes its structural, deformation, and strength properties. And there are some parameters that can influence time-dependent deformation and strength properties, such as mineral composition, stress level and history, pore fluid chemistry, drainage conditions, and fabric structure. It's very important to investigate strength and deformation characteristics of the soils because it gives us a great insight about the settlement, deformation, and the behavior in general of soils, and this can help analyze practical problems and predict the behavior of the soil in a long term. This is the first article that I chose, Long-Term Soaking Effect on Strength and Deformation Characteristics of a Gypsiferous Subgrade Soil. The foundation of every pavement is soil compacted, and it's called subgrade. It gives the adequate support to the pavement, so it's essential to study it. The article objective is to analyze the behavior of the California bearing ratio, CBR, the resilient modulus, and the deformation of compacted gypsiferous soil during long-term soaking. It simulates situations where groundwater table is very high or subgrade soil is subjected to a long-term flood. The soil studied in the article is a gypsiferous soil that is usually found in arid and semi-arid climates. In this case, it was obtained from a region near Baghdad. This soil has a high content of soluble salt. It represents 36% of the total dry weight, in which 94% is gypsum, calcium sulfate. It is a well-graded sand and silt, and according to ASHO classification, it is a A24 soil. In this first image, we can see the soil, and in this next one, we can clearly see the salt in the soil. To determine the effect of soaking on strength and deformation characteristics, 16 CBR samples were compacted following the ASHO CBR test specification. In this specification, it requires 4 days soaking, but in order to determine the effect of long-term soaking, 7 soaking periods were chosen: 4, 7, 15, 30, 60, 120, and 180 days. For each soaking period, a set of 2 CBR samples was tested. Ultrasonic pulse velocity technique was used to estimate the resilient modulus, and measurement of vertical movement was carried out during soaking CBR test. 2 CBR samples were tested unsoaked, and the result is relatively high. Here we can see it's about 56%. One explanation for it is that in dry conditions, the gypsum acts as a good cementing agent. With the increasing of soaking period, there is a decrease in CBR. With only 4 days of soaking, there was a reduction in CBR about 10%. The drop in CBR is very sharp in the beginning, and after about 2 weeks, it becomes less pronounced. The significant drop in CBR due to long-term soaking is associated with the dissolution of gypsum in water. Here, as expected, the resilient modulus follows the same pattern as CBR. There is a decrease more intense in the beginning, and it gets less intense after about 1 month. The resilient modulus appears to be less sensitive to the soaking period than CBR. We can note that the resilient modulus at the end of 180 soaking days is about 94% of the sample unsoaked, while CBR's is about 58%. One reason for it is that the CBR is greatly affected by softened soil at the top of sample during soaking, while the resilient modulus reflects the effect of the whole sample length. This graphic shows us the effect of soaking period on deformation of this Gypsiferous soil tested. Initially, the soil is partially saturated, having negative pore water pressure. This negative pore water pressure causes water to enter the soil from its top and bottom until it becomes fully saturated. Here in the graphic, we can see that the soil swells initially, and the maximum swelling occurs at about 20 days soaking period. Then it decreases gradually, indicating that settlement takes place at an increasing rate. Here, about the day 120, the settlement rate decreases, but the settlement continues to increase. This graphic also shows a significant effect of the soaking period on the deformation behavior of the soil. The conclusions of the article were that there was a significant decrease in CBR during soaking, and this decrease was very rapid initially and became progressively slower, so that after 180 soaking, the CBR value was 32%. The decrease in resilient modulus with soaking period is similar to, but much lower than that for the CBR, so that after 180 soaking, resilient modulus was 169 MPa. The soaking period has a significant effect on the deformation characteristics of Gypsiferous soil. The soil initially showed swelling, followed by settlement. Use of the 4-day soaking period is completely misleading, as suggests the ISO CBR test specification. It can lead to serious overestimation of soil strength and stiffness. Now let's talk about the second article. Long-term deformation of highway subgrade under coupling effect of traffic load and drying-wetting cycles. Here, to introduce the subject, I brought some information. Early methods for predicting the soil permanent deformation are based on empirical equations, numerical calculation model, or on finite element. They mainly concentrate on deformation of soil caused by traffic loads, and the effect of weather cyclic changes is seldom considered. Drying-wetting cycles due to weather changes inevitably have an influence on subgrade cumulative deformation. The article objective was to establish a new model to predict the cumulative deformation of compacted red clay subgrade with consideration of the effects of both traffic loads and drying-wetting cycles based on laboratory tests and numerical computation. To predict the subgrade long-term deformation, it was used the realistic vehicle uneven pavement subgrade coupling system method. It consists of 3 parts. The first part, called SP1, is the deformation induced by weather drying wetting cycles, which is affected by number of wetting and drying cycles and cycle amplitude. The deformation SP2 is composed of the deformation resulting from the attenuation of subgrade modules due to drying wetting cycles under the static loads, and the one caused by dissipation of pore water pressure under traffic loads. The SP3 deformation is a cumulative plastic deformation subjected to cyclic traffic loads. In this table, there are some physical properties of the red clay. The natural moisture content of the red clay is high, having a value of 58%. Its liquid limit is 73%, and these characteristics indicates that the red clay is of high plasticity. In order to study the performance of the compacted red clay as a subgrade, 3 axial shear tests were carried out to determine the compacted soil shear strength. The samples were compacted in 3 different degrees of compaction to evaluate the effect of it in the result. The samples were also tested on 3 amplitude values and 5 cycle times. Using the realistic vehicle uneven pavement subgrade coupling system method, the subgrade long-term deformation calculation model is given by this equation. To verify the accuracy of the proposed model, it was made a comparison of the test results with the values computed by the equation. It can be seen that the calculated values agree well with the test data, which demonstrate that the model proposed in this study gives a good prediction. Observing these two graphics, we can conclude that the cumulative plastic strain is different for each subgrade depth. It can be seen in this graphic that on the subgrade top surface we have the highest cumulative plastic strain. It is about 0.88%. And with increasing depth, the cumulative plastic strain decreases. And here in yellow we have the depth of 1 meter, and the cumulative plastic strain is about 0.03% strain value. From the other graphic, we can observe that the plastic strain increases as the number of load cycle increases for each depth. The growth rate is high at the early stage, and then gradually decreases and finally tends to stabilize. I think this graphic is very interesting because it shows us that the long-term deformation induced by dissipation of pore pressure is greater than the caused by cyclic loads at the initial stage. Here, with the increasing load cycles, the two deformation values will tend to be the same and to be stable. This graphic also shows us in green the long-term total deformation that is derived by the sum of these two deformations. And here we can see that the subgrade deformation could come up to something about 5.6 millimeters. That is a very high value. Contrasting these two graphics, it can be seen that the amplitude of drying wetting cycles has an apparent impact on the deformation, and this influence becomes much more significant under a large number of drying wetting cycles. On the other hand, the influence of subgrade compaction degree on the long-term deformation is slight. With this article, we concluded that the calculation model proposed in this study could give a precise prediction of red clay subgrade long-term deformation under the coupling effect of traffic load and drying wetting cycles. The cumulative plastic strain decreases as subgrade depth increases. The effect of pavement unevenness cannot be ignored for the reason that the plastic deformation generated by additional load is large. The deformation caused by dissipation of pore water pressure is larger than the traffic load induced deformation at the early stage. With the increasing number of load cycles, both of them tend to have the same value. Higher cycle amplitude leads to a higher subgrade long-term deformation, and this effect becomes more apparent at a high cycle time. The compaction degree has a slight impact on the subgrade deformation. Now I would like to compare the two articles. Both articles talk about time effects on soil, but the first article addresses about the long-term effect on strength and deformation, and the second article focuses only on deformation. The two articles highlight the importance of considering these effects on soil behavior prediction. And these two works criticize something. The first article criticized the actual CBR test specification because it recommends 4 days soaking on the CBR samples, but the conclusion of the article is that it could lead to misleading results. The second article criticized the methods of predicting the soil permanent deformation, and it proposes a new model. Both articles talk about specific types of soil. the first gypsiferous soil and the second red clay. And for future studies, I would like to propose apply and verify the conclusions of these both articles to all types of soil. That's all I have. Thank you for watching, and if you have any questions, please feel free to contact me. Bye bye. Thank you.